Part 1, Chapter 2 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Part 1 of Chapter 2. Chapter 2. Progress of Sidereal Astronomy. We now have to consider labors of a totally different character from those of Sir William Herschel. Exploration and discovery do not constitute the whole business of astronomy. The less adventurous, though not less arduous task of gaining a more and more complete mastery over the problems immemorially presented to her may, on the contrary, be said to form her primary duty. A knowledge of the movements of the heavenly bodies has, from the earliest times, been demanded by the urgent needs of mankind, and science finds its advantage, as in many cases it has taken its origin, in condescension to practical claims. Indeed, to bring such knowledge as near as possible to absolute precision has been defined by no mean authority as the true end of astronomy. Several causes concurred about the beginning of the last century to give a fresh and powerful impulse to investigations having this end in view. The rapid progress of theory almost compelled a corresponding advance in observation. Instrumental improvements rendered such an advance possible. Herschel's discoveries quickened the public interest in celestial inquiries. Royal, imperial, and grand-ducal patronage widened the scope of individual effort. The heart of the new movement was in Germany. Hitherto the observatory of Flamsteed and Bradley had been the acknowledged centre of practical astronomy. Greenwich observations were the standard of reference all over Europe, and the art of observing prospered in direct proportion to the fidelity with which Greenwich methods were imitated. Dr. Maskelyne, who had the post of Astronomer Royal during 46 years, from 1765 to 1811, was no unworthy successor to the eminent men who had gone before him. His foundation of the Nautical Almanac in 1767 alone constitutes a valid title to fame. He introduced at the observatory the important innovation of the systematic publication of results, and the careful and prolonged series of observations executed by him formed the basis of improved theories and corrected tables of the celestial movements, which were rapidly being brought to completion abroad. His catalogue of 36 fundamental stars was besides excellent in its way, and most serviceable. Yet he was devoid of Bradley's instinct for divining the needs of the future. He was fitted rather to continue a tradition than to found a school. The old ways were dear to him, and, indefatigable as he was, a definite purpose was wanting to compel him by its exigencies along the path of progress. Thus, for almost 50 years after Bradley's death, the acquisition of a small achromat (footnote 59) fitted to the old transit instrument, July 11, 1772, was the only notable change made in the instrumental equipment of the observatory. The transit, the zenith sector, and the mural quadrant, with which Bradley had done his incomparable work, retained their places long after they had become deteriorated by time and obsolete by the progress of invention. It was not until the very close of his career that Maskelyne, compelled by Pond's detection of serious errors, ordered Troughton's circle, which he did not live to employ. Meanwhile, the heavy national disasters with which Germany was overwhelmed in the early part of the 19th century seemed to stimulate rather than impede the intellectual revival already for some years in progress there. Astronomy was among the first of the sciences to feel the new impulse. By the efforts of Bode, Olbers, Schrödinger, and and von Zach, just and elevated ideas on the subject were propagated, intelligence was diffused, and a firm ground prepared for common action in mutual sympathy and disinterested zeal. They received powerful aid through the foundation, in 1804, by a young artillery officer named von Rickenbach of an optical and mechanical institute at Munich. Here the work of English instrumental artists was for the first time rivaled, and that of English opticians, when Fraunhofer entered the new establishment, far surpassed. The development given to the refracting telescope by this extraordinary man was indispensable to the progress of that fundamental part of astronomy which consists in the exact determination of the places of the heavenly bodies. Reflectors are brilliant engines of discovery, but they lend themselves with difficulty to the prosaic work of measuring right ascensions and polar distances. A signal improvement in the art of making and working flint glass thus most opportunely coincided with the rise of a German school of scientific mechanisms, to furnish the instrumental means needed for the reform which was at hand. Of the leader of that reform it is now time to speak. Friedrich Wilhelm Bessel was born at Minden in Westphalia, July 22, 1784. A certain taste for figures, coupled with a still stronger distaste for the Latin accidence, directed his inclination and his father's choice toward a mercantile career. In his 15th year, accordingly, he entered the house of Kulenkamp and Sons, in Bremen, as an apprenticed clerk. He was now thrown completely on his own resources. From his father, a struggling government official, heavily weighted with a large family, he was well aware that he had nothing to expect. His dormant faculties were roused by the necessity for self-dependence, and he set himself to push manfully forward along the path that lay before him. The post of supercargo on one of the trading expeditions sent from the Hanseatic towns to China and the East Indies was the aim of his boyish ambition, for the attainment of which he sought to qualify himself by the industrious acquisition of suitable and useful knowledge. He learned English in 2 or 3 months, picked up Spanish with casual aid of a gunsmith's apprentice, studied the geography of distant lands which he hoped to visit, collected information as to their climates, inhabitants, products, and the courses of trade. He desired to add some acquaintance with the art, then much neglected, of taking observations at sea, and thus led on from navigation to astronomy, and from astronomy to mathematics. He groped his way into a new world. It was characteristic of him that the practical problems of science should have attracted him before his mind was yet sufficiently matured to feel the charm of its abstract beauties. His first attempt at observation was made with a sextant, rudely constructed under his own direction, and a common clock. Its object was the determination of the longitude of Bremen, and its success, he tells us himself, filled him with a rapture of delight, which, by confirming his tastes, decided his destiny. He now eagerly studied Bode's Urbach and von Zach's Montelec correspondence, overcoming each difficulty as it arose with the aid of Lalande's Traité d'Astronomie, and supplying with amazing rapidity his early deficiency in mathematical training. In 2 years he was able to attack a problem which would have tasked the patience, if not the skill, of the most experienced astronomer. Amongst the Earl of Egremont's papers, von Zach had discovered Harriot's observations on Halley's comet at its appearance in 1607, and published them as supplement to Bode's Annal. With an elaborate care inspired by his youthful ardor, though hardly merited by their loose nature, Bessel deduced from them an orbit for that celebrated body, and presented the work to Olbers, whose reputation in cometary researches gave a special fitness to the proffered homage. The benevolent physician-astronomer of Bremen welcomed with surprised delight such performance emanating from such a source. 15 years previously, the French Academy had crowned a similar work. Now its equal was produced by a youth of 20, busily engaged in commercial pursuits, self-taught, and obliged to snatch from sleep the hours to devote to study. The paper was immediately sent to von Zach for publication, with a note from Olbers explaining the circumstances of its author, and the name of Bessel became the common property of learned Europe. He had, however, as yet no intention of adopting astronomy as his profession. For 2 years he continued to work in the counting-house by day, and to pore over the Mécanique Céleste and the differential calculus by night. But the post of assistant in Schroter's observatory at Lilienthal having become vacant by the removal of Harding to Göttingen in 1805, Olbers procured for him an offer of it. It was not without a struggle that he resolved to exchange the desk for the telescope. His reputation with his employers was of the highest. He had thoroughly mastered the details of the business, which his keen practical intelligence followed with lively interest. His years of apprenticeship were on the point of expiring, and an immediate and not unwelcome prospect of comparative affluence lay before him. The love of science, however, prevailed. He chose poverty and the stars, and went to Lilienthal with a salary of $100 a year. Looking back over his life's work, Olbers long afterwards declared that the greatest service which he had rendered to astronomy was that of having discerned, directed, and promoted the genius of Bessel. For 4 years he continued in Schroter's employment. At the end of that time, the Prussian government chose him to superintend the erection of a new observatory at Königsberg, which, after many vexatious delays, caused by the prostrate condition of the country, was finished toward the end of 1813. Königsberg was the first really efficient German observatory. It became, moreover, a centre of improvement, not for Germany alone, but for the whole astronomical world. During 32 years it was the scene of Bessel's labours, and Bessel's labours had for their aim the reconstruction, on an amended and uniform plan, of the entire science of observation. A knowledge of the places of the stars is the foundation of astronomy. Their configuration lends to the skies their distinctive features, and marks out the shifting tracks of more mobile objects with relatively fixed and generally unvarying points of light. A more detailed and accurate acquaintance with the stellar multitude, regarded from a purely uranographical point of view, has accordingly formed at all times a primary object of celestial science, and was, during the last century, cultivated with zeal and success, by which all previous efforts were dwarfed into insignificance. In Leland's Histoire Céleste, published in 1801, the places of no less than 47,390 stars were given, but in the rough, as it were, and consequently needing laborious processes of calculation to render them available for exact purposes. Piazzi set an example of improved methods of observation, resulting in the publication, in 1803 and 1814, of 2 catalogues of about 7,600 stars, the second being a revision and enlargement of the first, which for their time were models of what such work should be. Footnote 63. A new reduction of the observations upon which they were founded was undertaken in 1896 by Herman S. Davies of the U.S. Coast Survey. Stephen Groombridge at Blackheath was similarly and most beneficially active. But something more was needed than the diligence of individual observers. A systematic reform was called for, and it was this which Bessel undertook and carried through. Direct observation furnishes only what has been called the raw material of the positions of the heavenly bodies. A number of highly complex corrections have to be applied before their mean can be disengaged from their apparent places on the sphere. Of these, the most considerable and familiar is atmospheric refraction, by which objects seem to stand higher in the sky than they in reality do, the effect being evanescent at the zenith, and attaining, by gradations varying with conditions of pressure and temperature, a maximum at the horizon. Moreover, the points to which measurements are referred to themselves in motion, either continually in one direction or periodically to and fro. The precession of the equinoxes is slowly progressive, or rather retrogressive, the nutation of the pole oscillatory in a period of about 18 years. Added to which, the non-instantaneous transmission of light, combined with the movement of the earth in its orbit, causes a small annual displacement known as aberration. Now it is easy to see that any uncertainty in the application of these corrections saps the very foundations of exact astronomy. Extremely minute quantities, it is true, are concerned, but the life and progress of modern celestial science depends upon the sure recognition of extremely minute quantities. In these early years of the 19th century, however, no uniform system of reduction, so the complete correction of observational results is termed, had been established. Much was left to the individual caprice of observers, who selected for the several elements of reduction such values as seemed best to themselves. Hence arose much hurtful confusion, tending to hinder the united action and mar the usefulness of laborious researches. For this state of things Bessel, by the exercise of consummate diligence, sagacity, and patience, provided an entirely satisfactory remedy. His first step was an elaborate investigation of the precious series of observations made by Bradley at Greenwich from 1750 until his death in 1762. The catalogue of 3,222 stars, which he extracted from them, gave the earliest example of the systematic reduction on a uniform plan of such body of work. It is difficult, without entering into details out of place in a volume like the present, to convey an idea of the arduous nature of this task. It involved the formation of a theory of errors of each of Bradley's instruments, and a difficult and delicate inquiry into the true value of each correction to be applied, before the entries in the Greenwich journals could be developed into a finished and authentic catalogue. Although completed in 1813, it was not until 5 years later that the results appeared with the proud but not inappropriate title of Fundamenta Astronomiae. The eminent value of the work consisted in this, that providing a mass of entirely reliable information as to the state of the heavens at the epoch in 1755, it threw back the beginning of exact astronomy almost half a century. By comparison with Piazzi's catalogues, the amount of precession was more accurately determined. The proper motions of a considerable number of stars became known with certainty and definite prediction. The certificate of initiation into the secrets of nature at last became possible as regards the places of the stars. Bessel's final improvements in the methods of reduction were published in 1830 in his Tabula Regiomonte. They not only constituted an advance in accuracy, but afforded a vast increase of facility in application, and were at once and everywhere adopted. Thus astronomy became a truly universal science. Uncertainties and disparities were banished, and observations made at all times and places rendered mutually comparable. More, however, yet remained to be done. In order to verify the greater strictness with the results drawn from Bradley and Piazza's catalogues, a third term of comparison was wanted, and this Bessel undertook to supply. By a course of 75,011 observations executed during the years in 1821-33, with the utmost nicety of care, the number of accurately known stars was brought up to above 50,000, and an ample store of trustworthy facts laid up for the use of future astronomers. In this department, Argelander, whom he attracted from finance to astronomy and trained in his own methods, was his assistant and successor. The Great Bahn der Musterung, in which 324,198 stars visible in the northern hemisphere are enumerated, and the corresponding atlas, published in 1857-63, constituting a picture of our sidereal surroundings of heretofore unapproached completeness, may be justly said to owe their origin to Bessel's initiative, and to form a sequel to what he commenced. But his activity was not solely occupied with the promotion of a comprehensive reform in astronomy. It embraced special problems as well. The long-baffled search for a parallax of the fixed stars was resumed with fresh zeal, as each mechanical or optical improvement held out fresh hopes of a successful issue. Illusory results abounded. Piazza, in 1805, perceived, as he supposed, considerable annual displacements in Vega, Aldebaran, Sirius, and Procyon, the truth being that his instruments were worn out with constant use, and could no longer be depended upon. His countryman, Calandrielli, was similarly deluded. The celebrated controversy between Astronomer Royal and Dr. Brinkley, director of the Dublin College Observatory, turned on the same subject. Brinkley, who was in possession of a first-rate meridian circle, believed himself to have discovered relatively large parallaxes for 4 of the brightest stars. Pond, relying on the testimony of the Greenwich instruments, asserted their nullity. The dispute, protracted for 14 years, from 1810 until 1824, was brought to no definite conclusion, but strong presumption on the negative side was abundantly justified in the event. There was good reason for incredulity in the matter of parallaxes. Announcements of their detection had become so frequent as to be discredited before they were disproved, and Struve, who investigated the subject at Dorpat in 1818-21, had clearly shown that quantities concerned were too small to come within reliable measuring powers of any instrument then in use. Already, however, the means were being prepared of giving to those powers a large increase. On the 21st July, 1801, 2 old houses in an alley of Munich tumbled down, burying in their ruins the occupants, of whom one alone was extricated alive, though seriously injured. This was an orphan lad of 14 named Joseph Fraunhofer. The Elector Maximilian Joseph was witness of the scene, became interested in the survivor, and consoled his misfortune with a present of 18 ducats. Seldom was money better bestowed. Part of it went to buy books and a glass-polishing machine, with the help of which young Fraunhofer studied mathematics and optics, and secretly exercised himself in the shaping and finishing of lenses. The remainder of his purchase, his release from the tyranny of one Weisselberger, a looking-glass maker by trade, to whom he had been bound apprentice on the death of his parents. A period of struggle and privation followed, during which, however, he rapidly extended his acquirements, and thus was eminently fitted for the task awaiting him, when, in 1806, he entered the optical department of the establishment founded 2 years previously by von Rickenbach and Utenschneider. He now zealously devoted himself to the improvement of the achromatic telescope, and after a prolonged study of theory of lenses and many toilsome experiments in the manufacture of flint glass, he succeeded in perfecting, December 12, 1817, an object glass of exquisite quality and finish, 9½ inches in diameter and of 14 feet focal length. This, as it was then considered, gigantic lens was secured by Struve for the Russian government, and the great Dorpat refractor, the first of the large achromatics which have played such an important part in modern astronomy, was, late in 1824, set up in the place which it still occupies. By ingenious improvements in mounting and fitting, it was adapted to the finest micrometrical work, and thus offered unprecedented facilities both for the examination of double stars, in which Struve chiefly employed it, and for such subtle measurements as might serve to reveal or disprove the existence of a sensible stellar parallax. Fraunhofer, moreover, constructed for the observatory at Königsberg the first really available heliometer. The principle of this instrument, termed with more propriety a divided object-glass micrometer, is the separation by a strictly measurable amount of two distant images of the same object. If a double star, for instance, be under examination, the two half-lenses into which the object glass is divided are shifted until the upper star, say, in one image is brought into coincidence with the lower star in the other, when their distance apart becomes known by the amount of motion employed. Footnote 68. The heads of the screws applied to move the halves of the object glass in the Königsberg heliometer are of so considerable size that 1,000th part of a revolution, equivalent to 1/20th of a second of arc, can be measured with the utmost accuracy. This virtually new engine of research was delivered and mounted in 1829, 3 years after the termination of the life of its deviser. The Dorpat lens had brought Fraunhofer a title of nobility and the sole management of the Munich Optical Institute, completely separated since 1814 from the mechanical department. What he had achieved, however, was but a small part of what he meant to achieve. He saw before him the possibility of nearly quadrupling the light-gathering capacity of the great achromat acquired by Struve. He meditated improvements in reflectors, as important as those he had already effected in refractors, and was besides eagerly occupied with investigations into the nature of light, the momentous character of which we shall by and by have an opportunity of estimating. But his health was impaired, it is said, from the weakening effects of his early accident, combined with excessive and unwholesome toil, and still hoping for its restoration from a projected journey to Italy. He died of consumption, June 7, 1826, aged 39 years. His tomb in Munich bears the concise eulogy, "E proximavit sidera." Bessel had no sooner made himself acquainted with the exquisite defining powers of the Königsberg heliometer than he resolved to employ them in an attack upon the now secular problem of star distances. But it was not until 1837 that he found leisure to pursue the inquiry. In choosing his test star, he adopted a new principle. It had hitherto been assumed that our nearest neighbours in space must be found among the brightest ornaments of our skies. The knowledge of stellar proper motions afforded by the critical comparison of recent with earlier star places suggested a different criterion of distance. It is impossible to escape from the conclusion that the apparently swiftest moving stars are, on the whole, also the nearest to us, however numerous the individual exceptions to the rule. Now, as early as 1792, Piazzi had noted as an indication of relative vicinity to the Earth the unusually large proper motion, 5.2 minutes annually, of a double star of the fifth magnitude in the constellation of the Swan. Still more emphatically, in 1812, Bessel drew the attention of the astronomers to the fact, and 61 Cygni became known as the flying star. The seeming rate of its flight, indeed, is of so leisurely a kind that in 1,000 years it will have shifted its place by less than 3½ lunar diameters, and that 250,000 would be required to carry it round the entire circuit of the visible heavens. Nevertheless, it has few rivals in rapidity of movement, the apparent displacement of the vast majority of stars being, by comparison, almost insensible. This interesting, though inconspicuous object, then, was chosen by Bessel to be put to the question with his heliometer, while Struve made a similar and somewhat earlier trial with the bright gem of Lyre, whose Arabic title of the Falling Eagle survives as a time-worn remnant in Vega. Both astronomers agreed to use the differential method, for which their instruments, and the vicinity to their selected stars of minute, physically detached companions, offered special facilities. In the last month of 1838, Bessel made known the result of 1 year's observations, showing for 61 Cygni a parallax of about 1/3 of a second, 0.3136 minute. Footnote 71. It should be explained that what is called the annual parallax of a star is only half its apparent displacement. In other words, it is the angle subtended at the distance of that particular star by the radius of the Earth's orbit. He then had his heliometer taken down and repaired, after which he resumed the inquiry and finally terminated a series of 402 measures in March 1840. The resulting parallax of 0.3483 minutes, corresponding to a distance about 600,000 times that of the Earth from the Sun, seemed to be ascertained beyond the possibility of cavil, and is memorable as the first published instance of the fathom line, so industriously thrown into celestial space, having really and indubitably touched bottom. It was confirmed in 1842 through 43 with curious exactness by C. A. F. Peters at Pulkowa, but later researchers show that it required increase to nearly half a second. Struve's measurements inspired less confidence. They extended over 3 years, 1835 through 38, but were comparatively few and were frequently interrupted. The parallax, accordingly, of about 1/4 of a second, 0.2613 minutes, which he derived from them for Alpha Lyrae, and announced in 1840, has proved considerably too large. Footnote 75. Elkin's corrected result in 1897 for the parallax of Vega is 0.82 minutes. Meanwhile, a result of the same kind but a more striking character than either Bessel's or Struve's had been obtained, one might almost say casually, by a different method and in a distant region. Thomas Henderson, originally an attorney's clerk in his native town of Dundee, had become known for his astronomical attainments, and was appointed in 1831 to direct the recently completed observatory at the Cape of Good Hope. He began observing in April 1832, and the serious shortcomings of his instruments notwithstanding, executed during the 13 months of his tenure of office a surprising amount of first-rate work. With a view to correcting the declination of the lustrous double star Alpha Centauri, which ranks after Sirius and Canopus as the third brightest orb in the heavens, he effected a number of successive determinations of its position, and on being informed of its very considerable proper motion, 3.6 minutes annually, he resolved to examine the observations already made for possible traces of parallatic displacement. This was done on his return to Scotland, where he filled the office of Astronomer Royal from 1834 until his premature death in 1844. The result justified his expectations. From the declination measurements made at the Cape and duly reduced, a parallax of about 1 second of arc clearly emerged, diminished by Gill's and Elkin's observations, 1822 to 1883. to 0.75 minutes, but perhaps by an excess of caution was withheld from publication until fuller certainty was afforded by the concurrent testimony of Lieutenant Meadows' determinations of the same star's right ascension. When at last, January 9, 1839, Henderson communicated his discovery to the Astronomical Society, he could no longer claim the priority which was his due. Bessel had anticipated him with a parallax of 61 Cygni by just 2 months. Thus, from 3 different quarters, 3 successful and almost simultaneous assaults were delivered upon a long beleaguered citadel of celestial secrets. The same work has since been steadily pursued, with general results showing that as regards their overwhelming majority, the stars are far too remote to show even the slightest trace of optical shifting from the revolution of the earth in its orbit. In nearly 100 cases, however, small parallaxes have been determined, some certainly, that is, within moderate limits of error, others more or less precariously. The list is an instructive one in its omissions no less than in its contents. It includes stars of many degrees of brightness, from Sirius down to a nameless telescopic star in the Great Bear. Yet the vicinity to Earth of this minute object is so much greater than that of the brilliant Vega. Of the brightest stars are found to have no sensible parallax, while the majority of those ascertained to be nearest the Earth are of 5th, 6th, or even 9th magnitudes. The obvious conclusions follow that the range of variety in the sidereal system is enormously greater than had been supposed, and that estimates of distance based upon apparent magnitude must be wholly futile. Thus, the splendid Canopus, Betelgeuse, and Riyal can be inferred from their infinite remoteness to exceed our sun thousands of times in size and luster, while many inconspicuous objects, which prove to be in our relative vicinity, must be notably his inferiors. The limits of real stellar magnitude are then set very widely apart. At the same time, the so-called optical and geometrical methods of relatively estimating star distances are both seen to have a foundation of fact, although so disguised by complicated relations as to be of very doubtful individual application. On the whole, the chances are in favor of the superior vicinity of a bright star over a faint one, and, on the whole, the stars in swiftest apparent motion are among those whose actual remoteness is least. Indeed, there is no escape from either conclusion, unless on a supposition of special arrangements in themselves highly improbable, and we may confidently say non-existent. End of Part 1, Chapter 2. Part 2, Chapter 2 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke, Part 2 of Chapter 2. The distances, even of the few stars found to have measurable parallaxes, are on a scale entirely beyond the powers of the human mind to conceive. In the attempt to both realize them distinctly and to express them conveniently, a new unit of length, itself of bewildering magnitude, has originated. This is what we may call the light journey of 1 year. The subtle vibrations of the ether, propagated on all sides from the surfaces of luminous bodies, travel at the rate of 186,300 miles a second, or in round numbers, 6 billions of miles a year. 4 1/3 such measures are needed to span the abyss that separates us from the nearest fixed star. In other words, light takes 4 years and 4 months to reach the earth from Alpha Centauri. Yet Alpha Centauri lies some 10 billions of miles nearer to us, so far as it is yet known, than any other member of the sidereal system. The determination of parallax leads, in the case of stars revolving in known orbits, to the determination of mass. For the distance from the Earth of the two bodies forming a binary system being ascertained, the seconds of arc apparently separating them from each other can be translated into millions of miles, and we only need to add a knowledge of their period to enable us, by an easy sum in proportion, to find their combined mass in the terms of that sun. Thus, since according to Dr. Dobrik's elements, the components of Alpha Centauri revolve around their common center of gravity at a mean distance nearly 25 times the radius of the Earth's orbit in a period of 88 years, the attractive force of the two together must be just twice the solar. We may gather some idea of their relations by placing in imagination a second luminary like our Sun in circulation between the orbits of Neptune and Uranus. But systems of still more majestic proportions are reduced by extreme remoteness to apparent insignificance. A double star of the 4th magnitude in Cassiopeia, Eta, to which a small parallax is ascribed on the authority of O. Struve, appears to be above 8 times as massive as the central orb of our world, while a much less conspicuous pair, 85 Pegasi, exerts, if the available data can be depended upon, no less than 13 times the solar gravitating power. Further, the actual rate of proper motions, so far as regards that part of them which is projected upon the sphere, can be ascertained for stars at known distance. The annual journey, for instance, of 61 Cygni across the line of sight amounts to 1,000, and that of Alpha Centauri to 446 millions of miles. A small star, numbered 1,830 in Grunberg's circumpolar catalogue, devours the way at the rate of at least 150 miles a second, a speed, in Newcomb's opinion, beyond the gravitating power of the entire sidereal system to control. And Mu Cassiopeia possesses above 2/3 of that surprising velocity, while for both objects radial movements of just 60 miles a second were disclosed by Professor Campbell's spectroscopic measurements. Herschel's conclusion as to the advance of the sun among the stars was not admitted as valid by the most eminent of his successors. Bessel maintained that there was absolutely no preponderating evidence in favor of its supposed direction toward a point in the constellation of Hercules. Biot, Burckhardt, and even Herschel's own son shared his incredulity. But the appearance of Argelander's prize essay in 1837 changed the aspect of the question. Herschel's first memorable solution in 1783 was based upon the motions of 13 stars, imperfectly known. His second, in 1805, upon those of no more than 6. Argelander now obtained an entirely concordant result from the large number of 390, determined with a scrupulous accuracy characteristic of Bessel's work and his own. The reality of the fact thus persistently disclosed could no longer be doubted. It was confirmed 5 years later by the younger Struve, and still more strikingly in 1847 by Galloway's investigations, founded exclusively on the apparent displacements of the southern stars. In 1859 and 1863, Sir George Airy and Mr. Duncan, 1821 through 1898, employing all the resources of modern science and commanding the wealth of material furnished by 1,167 proper motions carefully determined by Bisner Main, reached conclusions closely similar to that indicated nearly 80 years previously by the first great sidereal astronomer, which Mr. Plummer's re-investigation of the subject in 1883 served but slightly to modify. Yet astronomers were not satisfied. Dr. Auwers of Berlin completed in 1866 a splendid piece of work for which he received in 1888 the gold medal of the Royal Astronomical Society. It consisted in reducing afresh, with the aid of the most refined modern data, Bradley's original stars, and comparing their places thus obtained for the year 1755 with those assigned to them from the observations made at Greenwich after the lapse of 90 years. In the interval, as was to be anticipated, most of them were found to have travelled over some small span of the heavens, and there resulted a stock of nearly 3,000 highly authentic proper motions. These ample materials were turned to account by M. Ludwig Struve for a discussion of the sun's motion, of which the upshot was to shift its point of aim to the bordering region of the constellation of Hercules and Lyra, and the more easterly position of the solar apex was fully confirmed by the experiments, with variously assorted lists of stars, of Louis Boss of Albany, Oscar Stump of Bonn. Fresh precautions of refinement were introduced into the treatment of the subject by Ristenpart of Karlsruhe, by Kapteyn of Groningen, and Newcomb and Porter in America, who ably availed themselves of the copious materials accumulated before the close of the century. Their results, although not more closely accordant than those of their predecessors, combined to show that the journey of our system is directed towards a point within a circle about 10 degrees in the radius, having the brilliant Vega for its centre. To determine its rate was a still more arduous problem. It involved the assumption, very much at discretion, of an average parallax for the stars investigated, and Otto Struve's estimate of 154 million miles as the span yearly traversed was hence wholly unreliable. Fortunately, however, as will be seen further on, a method of determining the sun's velocity independently of any knowledge of star distances has now become available. As might have been expected, speculation has not been idle regarding the purpose and goal of the strange voyage of discovery through space upon which our system is embarked, but altogether fruitlessly. The variety of the conjectures hazarded in the matter is in itself a measure of their futility. Long ago, before the construction of the heavens had as yet been made the subject of methodical inquiry, Kant was disposed to regard Sirius as the central sun of the Milky Way, while Lambert surmised that the vast Orion nebula might serve as the regulating power of a subordinate group, including our sun. Herschel threw out the hint that the great cluster in Hercules might prove to be the supreme seat of attractive force. Argelander placed his central body in the constellation Perseus. Fomalhaut, the brilliant of the southern fish, was set in the post of honor by Bugulowski of Breslau. Madler, who succeeded Struve at Dorpat in 1839, concluded from a more formal inquiry that the ruling power in the sidereal system resided not in any single preponderating mass, but in the centre of gravity of the self-controlled revolving multitude. In the former case, as we know from the example of the planetary scheme, the stellar motions would be most rapid near the centre, and the latter they would become accelerated with remoteness from it. Mädler showed that no part of the heavens could be indicated as a region of exceptionally swift movements, such as would result from the presence of a gigantic, though possibly obscure, ruling body, but that a community of extremely sluggish movements undoubtedly existed in and near the group of the Pleiades, where, accordingly, he placed the center of gravity of the Milky Way. The bright star Halcyon thus became the central sun, but in a purely passive sense, its headship being determined by its situation at the point of neutralization of opposing tendencies, and of consequent rest. By an avowedly conjectural method, the solar period of revolution round this point was fixed at 18,200,000 years. The scheme of sidereal government framed by the Dorpat astronomer was, it may be observed, of the most approved constitutional type, deprivation rather than increase of influence accompanying the office of chief dignitary. But while we are still ignorant, and shall perhaps ever remain so, of the fundamental plan upon which the galaxy is organized, recent investigations tend more and more to exhibit it, not as a monarchical, so to speak, but as federative. The community of proper motions detected by Mädler in the vicinity of the Pleiades may accordingly possess a significance altogether different from what he imagined. Bessel's so-called Foundation of an Astronomy of the Invisible now claims attention. His prediction regarding the planet Neptune does not belong to the present division of our subject. A strictly analogous discovery in the sidereal system was, however, also very clearly foreshadowed by him. His earliest suspicions of non-uniformity in the proper motion of Sirius dated from 1834. They extended to Procyon in 1840, and after a series of refined measurements with the new Repsode circle, he announced in 1844 his conclusion that these irregularities were due to the presence of obscure bodies round which two bright dog stars revolved as they pursued their way across the sphere. He even assigned to each an approximate period of half a century. I adhere to the conviction, he wrote later to Humboldt, that Procyon and Sirius form real binary systems, consisting of a visible and an invisible star. There is no reason to suppose luminosity is an essential quality of cosmical bodies. The visibility of countless stars is no argument against the invisibility of countless others. An inference so contradictory to received ideas obtained little credit, until Peters found, in 1851, that the apparent anomalies in the movements of Sirius could be completely explained by an orbital revolution in a period of 50 years. Bessel's prevision was destined to be still more triumphantly vindicated. On the 31st of January, 1862, while in the act of trying a new 18-inch refractor, Mr. Alvin G. Clerke, one of the celebrated firm of American opticians, actually discovered the hypothetical Sirian companion in the precise position required by theory. It has now been watched through nearly an entire revolution, period of 49.4 years, and proves to be very slightly luminous in its proportion to its mass. Its attractive power, in fact, is nearly half that of its primary, while it emits only 1/10,000th of its light. Sirius itself, on the other hand, possesses a far higher radiative intensity than our sun. It gravitates, emitting Sir David Gill's parallax of 0.38 minutes to be exact, like two suns, but shines like 20. Possibly is much distended by heat, and undoubtedly its atmosphere intercepts a very much smaller proportion of its light than in stars of the solar class. As regards Procyon, visual verification was awaited until November 13, 1896, when Professor Schaeberle, with a great Lick refractor, detected the long-sought object in the guise of a 13th magnitude star. Dr. C's calculations showed it to possess 1/5 of the mass of its primary, or rather more than half of that of our sun. Yet it gives barely 1/20,000th of the sun's light, so that it is still nearer to total obscurity than the dusky satellite of Sirius. The period of 40 years assigned to the system by Owens in 1862 appears to be singularly exact. But Bessel was not destined to witness the recognition of the invisible as a legitimate and profitable field for astronomical research. He died March 17, 1846, just 6 months before the discovery of Neptune, of an obscure disease, eventually found to be occasioned by an extensive fungus growth in the stomach. The place which he left vacant was not an easy one to fill. His life's work might truly be described as epoch-making. Rarely, indeed, shall we find one who reconciled with the same success the claims of theoretical and practical astronomy, or surveyed the science which he had made his own with a glance equally comprehensive, practical, and profound. The career of Friedrich Georg Wilhelm Struve illustrates the maxim that science differentiates as it develops. He was, while much besides, a specialist in double stars. His earliest recorded use of the telescope was to verify Herschel's conclusion as to the revolving movement of Castor, and he never varied from the predilection which his first observation at once indicated and determined. He was born at Altona of a respectable yeoman family, April 15, 1793. And in 1811 he took a degree in philology at the new Russian University of Dorpat. He then turned to science, was appointed in 1813 to a professorship of astronomy and mathematics, and began regular work in the Dorpat Observatory, just erected by Parrot for Alexander I. It was not, however, until 1819 that the acquisition of a 5-foot refractor by Troughton enabled him to take the position angles of double stars with regularly and tolerable precision. The resulting catalogue of 795 stellar systems gave the signal for a general resumption of the Herschelian labours in his branch. The resulting catalogue of 795 stellar systems gave the signal for a general resumption of Herschelian labours in this branch. His success so far, and the extraordinary facilities for observation afforded by the Fraunhofer achromatic, encouraged him to undertake, February 11, 1825, a review of the entire heavens down to 5 degrees south of the celestial equator, which occupied more than 2 years, and yielded, from an examination of above 120,000 stars, a harvest of about 2,200 previously unnoticed composite objects. The ensuing 10 years were devoted to delicate and patient measurements, the results of which were embodied in Mensura Micrometrica, published at St. Petersburg in 1837. This monumental work gives the places, angles of position, distances, colors, and relative brightness of 3,112 double and multiple stars, all determined with utmost skill and care. The record is one which gains in value with the process of time and will for ages serve as a standard of reference by which to detect change or confirm discovery. It appears from Struve's researches that about 1 in 40 of all stars down to the 9th magnitude is composite, but that the proportion is doubled in the brighter orders. This he attributed to the difficulty of detecting the faint companions in very remote orbs. It was also noticed, both by him and Bessel, that double stars are in general remarkable for large proper motions. Struve's catalogue included no star of which the components were more than 32 minutes apart, because beyond that distance the chances of merely optical juxtaposition become considerable. But the immense preponderance of extremely close over, as it were, loosely yoked bodies is such as to demonstrate their physical connection, even if no other proof were forthcoming. Many stars, previously believed to be single, divided under the scrutiny of the Dorpat refractor, while in some cases one member of a supposed binary system revealed itself as double, thus placing the surprised observer in the unexpected presence of a triple group of suns. 5 instances were noted of 2 pairs lying so close together as to induce conviction of their mutual dependence, besides which 124 examples occurred of triple, quadruple, and multiple combinations, the reality of which was open to no reasonable doubt. It was first pointed out by Bessel that the fact of stars exhibiting a common proper motion might serve as an unfailing test of their real association into systems. This was, accordingly, one of the chief criteria employed by Struve to distinguish true binaries from merely optical couples. On this ground alone, 61 Cygni was admitted to be a genuine double star, and it was shown that although its components appeared to follow almost strictly rectilinear paths, yet the probability of their forming a connected pair is actually greater than the sun rising tomorrow morning. Moreover, this tie of an identical movement was discovered to unite bodies far beyond the range of distance ordinarily separating the members of binary systems, and to prevail so extensively as to lead to the conclusion that single do not outnumber conjoined stars more than twice or thrice. In 1835, Struve was summoned to the Emperor Nicholas to superintend the erection of a new observatory at Pulkowa near St. Petersburg, destined for the special cultivation of sidereal astronomy. Boundless resources were placed at his disposal, and the institution created by him was acknowledged to surpass all others of its kind in splendor, efficiency, and completeness. Its chief instrumental glory was a refractor of 15 inches aperture by Merz and Mahler, Fraunhofer's successors, which left the famous Dorpat telescope far behind, and remained long without rival. On the completion of this model establishment, August 19, 1839, Struve was installed as its director, and continued to fulfill the important duties of the post with his accustomed vigor until 1858, when illness compelled his virtual resignation in favor of his son Otto Struve, born at Dorpat, 1819. He died November 23, 1864. An inquiry into the laws of stellar distribution, undertaken during the early years of his residence at Pulkowa, led Struve to confirm, in the main, the inferences arrived at by Herschel as to the construction of the heavens. According to his view, the appearance known as the Milky Way is produced by a collection of irregularly condensed star clusters, within which the sun is somewhat eccentrically placed. The nebulous ring which thus integrates the light of countless worlds was supposed by him to be made up of stars scattered over a bent or broken plane, or to lie in two planes slightly inclined to each other, our system occupying a position near the intersection. He further attempted to show that the limits of this vast assemblage must remain forever shrouded from human discernment, owing to the gradual extinction of light in its passage through space, and sought to confer upon this celebrated hypothesis a definiteness and certainty far beyond the aspirations of its earlier advocates, Cheseaux and Olbers. But arbitrary assumptions vitiated his reasonings on this, as well as on some other points. In his special line as a celestial explorer of the most comprehensive type, Sir William Herschel had but one legitimate successor, and that successor was his son. Jean Friedrich William Herschel was born at Slough, March 17, 1792, graduated with the highest honours from St. John's College, Cambridge, in 1813, and entered upon legal studies with a view to being called to the bar. But his share in an early compact with Peacock and Babbage to do their best to leave the world wiser than they found it was not thus to be fulfilled. The acquaintance of Dr. Wollaston decided his scientific vocation. Already, in 1816, we find him reviewing some of his father's double stars, and he completed in 1820 the 18-inch speculum which was to be the chief instrument of his investigations. Soon afterwards he undertook, in conjunction with Mr. later Sir James South, a series of observations, issuing in the presentation to the Royal Society of a paper containing micrometrical measurements of 380 binary stars, by which the elder Herschel's inferences of orbital motion were in many cases strikingly confirmed. A star in the northern crown, for instance, Eta Corona, had completed more than one entire circuit since its first discovery. Another, Tau Ophiuchi, had closed up into apparent singleness, while the motion of a third, Xi Ursa Majoris, in an obviously eccentric orbit, was so rapid as to admit of being traced and measured from month to month. It was from the first confidently believed that the force retaining double stars in curvilinear paths was identical with that governing planetary revolutions. But that identity was not ascertained until Savary of Paris showed, in 1827, that the movements of the above-named binary in the Great Bear could be represented with all attainable accuracy by an eclipse calculated on orthodox gravitational principles with a period of 58 1/4 years. Inck followed Berlin with a still more elegant method, and Sir John Herschel, pointing out the uselessness of analytical refinements where the data were necessarily so imperfect, described in 1832 a graphical process by which the aid of the eye and hand was brought in to guide the judgment in a case where judgment only and not calculation could be of any avail. Improved methods of the same kind were published by Dr. C. in 1893 and by Dr. Burnham in 1894, and our acquaintance with stellar orbits is steadily gaining precision, certainty, and extent. In 1825 Herschel undertook and executed with great assiduity during the ensuing 8 years a general survey of the northern heavens, directed chiefly toward the verification of his father's nebular discoveries. The outcome was a catalogue of 2,306 nebulae and clusters, of which 525 were observed for the first time, besides 3,347 double stars discovered almost incidentally, strongly invited, as he tells us himself, by the peculiar interest of the subject and the wonderful nature of the objects which presented themselves. He resolved to attempt the completion of the survey in the southern hemisphere. With this noble object in view, he embarked his family and instruments on board the Mount Stuart Elphinstone, and after a prosperous voyage landed at Cape Town on the 16th of January, 1834. Choosing as the scene of his observations a rural spot under the shelter of Table Mountain, he began regular sweeping on the 5th of March. The site of his great reflector is now marked with an obelisk, and the name Feldhausen has become memorial in the history of science, for the 4 years' work done there may truly be said to open the chapter of our knowledge as regards the southern skies. The full results of Herschel's journey to the Cape were not made public until 1847, when a splendid volume, Results of Astronomical Observation, made during the years 1834–8 at the Cape of Good Hope, embodying them, was brought out at the expense of the Duke of Northumberland. They form a sequel to his father's labors, such as the investigations of one man may have rarely received from those of another. They form a sequel to his father's labors, such as the investigations of one man have rarely received from those of another. What the elder observer did for the northern heavens, the younger did for the southern, and with generally concordant results. Reviving the paternal method of star gauging, he showed from a count of 2,299 fields that the Milky Way surrounds the solar system as a complete annulus of minute stars, not, however, quite symmetrically, since the sun was thought to lie somewhat nearer to those portions visible in the southern hemisphere, which display a brighter lustre and a more complicated structure than the northern branches. The singular cosmical agglomerations known as the Magellanic Clouds were now for the first time submitted to a detailed, though admittedly incomplete, examination, the almost inconceivable richness and variety of their contents being such that a lifetime might with great profit be devoted to their study. In the greater Nubecula, within a compass of 42 square degrees, Herschel reckoned 278 distinct nebulae and clusters, besides 50 or 60 outliers, and a large number of stars intermixed with diffused nebulosity, in all 919 catalogued objects, and for the lesser cloud 244. Yet this was only the most conspicuous part of what his 20-foot revealed. Such an extraordinary concentration of bodies, so various, led him to the inevitable conclusion that the nebulae are to be regarded as systems sui generis, and which have no analogues in our hemisphere. He also noted the blankness of surrounding space, especially in the case of Nubecula Minor, the access to which all sides, he remarked, is through a desert, as if the cosmical material in the neighborhood had been swept up and garnered in these mighty groups. Of southern double stars, he discovered and gave careful measurements of 2,102, and described 1,708 nebulae, of which at least 300 were new. The list was illustrated with a number of drawings, some of them extremely beautiful and elaborate. Sir John Herschel's views as to the nature of nebula were considerably modified by Lord Rosse's success in resolving, with his great reflectors, a crowd of these objects into stars. His former somewhat hesitating belief in the existence of phosphorescent matter, disseminated through extensive regions of space in the manner of a cloud or fog, was changed into a conviction that no valid distinction could be established between the faintest wisp of cosmical vapor just discernible in a powerful telescope and the most brilliant and obvious cluster. He admitted, however, an immense range of possible variety in the size and mode of aggregation of the stellar constituents of various nebulae. Some might appear nebulous from the closeness of their parts, some from their smallness. Others, he suggested, might be formed of discrete luminous bodies floating in a non-luminous medium, while the annular kind probably consisted of hollow shells of stars. That a physical and not merely optical connection unites nebulae with the embroidery, so to speak, of small stars, with which they are in many instances profusely decorated, was evident to him, as it must be to all who look as closely and see as clearly as he did. His description of number 2093 in his Northern Catalogue as a network or tracery of nebula following the lines of a similar network of stars would alone suffice to dispel the idea of accidental scattering, and many other examples of a like import might be quoted. The remarkably frequent occurrence of one or more minute stars in the close vicinity of planetary nebulae led him to infer their dependent condition, and he advised the maintenance of a strict watch for evidences of circulatory movements, not only over these supposed stellar satellites, but also over the numerous double nebulae, in which, as he pointed out, all the varieties of double stars as to distance, position, and relative brightness have their counterparts. He moreover investigated the subject of nebular distribution by the simple and effectual method of graphic delineation or charting, and succeeded in showing that while a much greater uniformity of scattering prevails in the southern than in the northern heavens, a condensation is nevertheless perceptible about the constellations Pisces and Cetus, roughly corresponding to the nebular region in Virgo, by its vicinity, within 20 degrees or 30 degrees, to the opposite pole of the Milky Way. He concluded that the nebulous system is distinct from the sidereal, though involving and perhaps to a certain extent intermixed with the latter. Towards the close of his residence at Feldhausen, Herschel was fortunate enough to witness one of those singular changes in the aspect of the firmament which occasionally challenges the attention even of the incurious, and excite the deepest wonder of the philosophical observer. Immersed apparently in the Argo Nebula is a star denominated Eta Carinea. When Halley visited St. Helena in 1677, it seemed of the 4th magnitude, but Leucel, in the middle of the following century, and others after him, classed it as of the 2nd. In 1827, the traveller Burchell, being then at St. Paul, near Rio de Janeiro, remarked that it had unexpectedly assumed the 1st rank, a circumstance the more surprising to him because he had frequently, when in Africa during the years 1811 to 1815, noted it as only of the 4th magnitude. This observation, however, did not become generally known until later. Herschel, on his arrival at Feldhausen, registered the star as a bright second, and had no suspicion of its unusual character until December 16, 1837, when he suddenly perceived its light to be almost tripled. It then far outshone Rigel in Orion, and on the 2nd of January following it very nearly matched Alpha Centauri. From that date it declined, but a second and even brighter maximum occurred in April 1843, when Maclear, then director of the Cape Observatory, saw it blaze out with a splendor approaching that of Sirius. Its waxings and wanings were marked by curious trepidations of brightness, extremely perplexing to theory. In 1863 it had sunk below fifth magnitude, and in 1869 was barely visible to the naked eye. Yet it was not until 18 years later that it touched a minimum of 7.6 magnitude. Soon afterwards a recovery of brightness set in, but was not carried very far, and the star now shines steadily as of the seventh magnitude, its reddish light contrasting effectively with the silvery rays of the surrounding nebula. An attempt to include its fluctuations within a cycle of 70 years has signally failed, the extent and character of the vicissitudes to which it is subject stamping it rather as a species of connecting link between periodic and temporary stars. Among the numerous topics which engaged Herschel's attention at the Cape was that of relative stellar brightness. Having contrived an astrometer in which an artificial star, formed by the total reflection of moonlight from the base of a prism, served as a standard of comparison, he was able to estimate the lustre of the natural stars examined by the distances at which artificial objects appeared equally respective to each. He thus constructed a table of 191 principal stars, both in the northern and southern hemispheres, setting forth the numerical values of their apparent brightness relative to that of Alpha Centauri, which he selected as a unit of measurement. Further, the light of the full moon being found to him to exceed that of a standard star 27,408 times, and Dr. Wollaston having shown that the light of the full moon is to that of the sun as 1 to 801,072. Zoller made the ratio 1 to 618,000. It becomes possible to compare stellar with solar radiance. Hence was derived, in the case of the few stars that ascertain distances, a knowledge of real luster. Alpha Centauri, for example, emits less than twice, Capella 100 times as much light as our sun, while Arcturus, at its enormous distance, must display a splendor of 1,300 such luminaries. Herschel returned to England in the spring of 1838, bringing with him a wealth of observation and discovery such as had perhaps never been before amassed in so short a time. Deserved honours awaited him. He was created a baronet on the occasion of the Queen's coronation. He had been knighted in 1831. Universities and learned societies vied with each other in showering distinctions upon him, and the success of an enterprise in which scientific zeal was tinctured with attractive flavour of adventurous romance was justly regarded as a matter of national pride. His career as an observing astronomer was now virtually closed, and he devoted his leisure to the collection and arrangement of the abundant trophies of his fathers and his own activity. The resulting great catalogue of 5,079 nebulae, including all then certainly known, published in the Philosophical Transactions for 1864, is, and will probably long remain, the fundamental source of information on the subject. Footnote 129. Dr. Dreyer's New General Catalogue, published in 1888, volume XLIX of the Royal Astronomical Society's Memoirs, is an enlargement of Herschel's work. It includes 7,840 entries and was supplemented in 895 by an index catalogue of 1,529 nebulae discovered in 1888 to 1894. But he unfortunately did not live to finish the companion work on double stars, for which he had accumulated a vast store of materials. The consideration of Sir John Herschel's Cape observations brings us to the close of the period which we are now engaged in studying. They were given to the world, as already stated, 3 years before the middle of the century, and accurately represent the condition of sidereal science at that date. Looking back over the 50 years traversed, we can see at a glance how great was the stride made in the interval. Not alone was acquaintance with individual members of the cosmos vastly extended, but their mutual relations, the laws governing their movements, their distances from the earth, masses, and intrinsic luster, had begun to be successfully investigated. Begun to be, for only regarding a scarcely perceptible minority had even approximate conclusions been arrived at. Nevertheless, the whole progress of the future lay in that beginning. It was the thin end of the wedge of exact knowledge. The principle of measurement had been substituted for that of probability. A basis had been found for large and strong enough to enable calculation to ascend from it to the sidereal heavens, and refinements had been introduced, fruitful in performance, but still more in promise. Thus, rather the kind than the amount of information collected was significant for the time to come. Rather the methods employed than the results actually secured rendered the first half of the 19th century of epochal importance in the history of our knowledge of the stars. End of Part 1, Chapter 2.
Part 5, Chapter 3 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Chapter 3, Part 1. Progress of Knowledge Regarding the Sun. The discovery of sunspots in 1610 by Fabricius and Galileo first opened a way for inquiry into the solar constitution, but it was long before that way was followed with system or profit. The seeming irregularity of the phenomena discouraged continuous attention. Casual observations were made the basis of arbitrary conjectures, and real knowledge received little or no increase. In 1620 we find Jean Tarde, canon of Sarlat, arguing that because the sun is the eye of the world, and the eye of the world cannot suffer from ophthalmia, therefore the appearances in question must be due, not to actual specks or stains on the bright solar disk, but to the transits of a number of small planets across it. To this new group of heavenly bodies he gave the name of Barbonia Sidera, and they were claimed in 1633 for the House of Habsburg, under the title of Austriaca Sidera, by Father Malipertius, a Belgian Jesuit. A similar view was temporarily maintained against Galileo by the justly celebrated Father Scheiner of Ingolstadt, and later by William Gascoigne, the inventor of the micrometer. But most of those who were capable of thinking at all on such subjects, and they were but few, adhered either to the cloud theory or to the slag theory of sunspots. The first was championed by Galileo, the second by Simon Marius, astronomer and physician to the brother Margraves of Brandenburg. The latter opinion received a further notable development from the fact that in 1618, a year remarkable for the appearance of 3 bright comets, the sun was almost free from spots, whence it was inferred that the cindery refuse from the great solar conflagration, which usually appeared as dark blotches on its surface, was occasionally thrown off in the form of comets, leaving the sun, like a snuffed taper, to blaze with renewed brilliancy. In the following century, Derham, gathered from observations carried on during the years 1703 to 1711, that the spots on the sun are caused by the eruption of some new volcano therein, which at first pouring out a prodigious quantity of smoke and other opacous matter, causeth the spots; and as that fuliginous matter decayeth and spendeth itself, and the volcano at last becomes more torrid and flaming, so the spots decay and grow to umbrae, and at last to faculae. The view, confidently upheld by Lalande, that spots were rocky elevations uncovered by the casual ebbing of a luminous ocean, the surrounding penumbrae representing shoals or sandbanks, had even less to recommend it than Derham's volcanic theory. Both were, however, significant of a growing tendency to bring solar phenomena within the compass of terrestrial analogies. For 164 years, then, after Galileo first leveled his telescope at the setting sun, next to nothing was learned as to its nature, and the facts immediately ascertained of its rotation on an axis nearly erect to the plane of the ecliptic, in a period of between 25 and 26 days, and of the virtual limitation of the spots to a so-called royal zone extending some 30° north and south of the solar equator, gained little in either precision or development from 5 generations of astronomers. But in November 1769 a spot of extraordinary size engaged the attention of Alexander Wilson, professor of astronomy in the University of Glasgow. He watched it day by day, and to good purpose. As the great globe slowly revolved, carrying the spot toward its western edge, he was struck with the gradual contraction and final disappearance of the penumbra on the side next to the center of the disk; and when on the 6th of December the same spot re-emerged on the eastern limb, he perceived, as he had anticipated, that the shady zone was now deficient on the opposite side, and resumed its original completeness as it returned to a central position. In other spots subsequently examined by him, similar perspective effects were visible, and he proved in 1774, by strict geometrical reasoning, that they could only arise in vast photospheric excavations. It was not, indeed, the first time that such a view had been suggested. Father Scheiner's later observations plainly foreshadowed it. A conjecture to the same effect was emitted by Leonard Rost of Nuremberg early in the 18th century. Both by Lahire in 1703 and by J. Cassini in 1719, spots had been seen as notches on the solar limb, while in 1770 Pastor Schulin of Essingen, from the careful study of phenomena similar to those noted by Wilson, concluded their depressed nature. Modern observations, nevertheless, prove those phenomena to be by no means universally present. Wilson's general theory of the sun was avowedly tentative. It took the modest form of an interrogatory. "Is it not reasonable to think," he asks, "that the great and stupendous body of the sun is made up of 2 kinds of matter, very different in their qualities; that by far the greater part is solid and dark, and that this immense and dark globe is encompassed with a thin covering of that resplendent substance from which the sun would seem to derive the whole of its vivifying heat and energy?" He further suggests that the excavations or spots may be occasioned by the working of some sort of elastic vapor which is generated within the dark globe, and that the luminous matter, being in some degree fluid, and being acted upon by gravity, tends to flow down and cover the nucleus. From these hints, supplemented by his own diligent observations and sagacious reasonings, Herschel elaborated a scheme of solar constitution which held its ground until the physics of the sun were revolutionized by the spectroscope. A cool, dark, solid globe, its surface diversified with mountains and valleys, clothed in luxuriant vegetation and richly stored with inhabitants, protected by a heavy cloud canopy from the intolerable glare of the upper luminous region, where the dazzling coruscations of a solar aurora some thousands of miles in depth evolved the stores of light and heat which vivify our world. Such was the central luminary which Herschel constructed with his wonted ingenuity and described with his wonted eloquence. "This way of considering the sun and its atmosphere," he says, "removes the great dissimilarity we have hitherto been used to finding between its condition and that of the rest of the great bodies of the solar system. The sun, viewed in this light, appears to be nothing else than a very eminent, large, and lucid planet, evidently the first, or, in strictness of speaking, the only primary one of our system, all others being truly secondary to it. Its similarity to other globes of the solar system with regard to its solidity, its atmosphere, and its diversified surface, the rotation upon its axis, and the fall of heavy bodies, leads us on to suppose that it is most probably also inhabited, like the rest of the planets, by beings whose organs are adapted to the peculiar circumstances of that vast globe. We smile at conclusions which our present knowledge condemns as extravagant and impossible, but such incidental flights of fancy in no way derogate from the high value of Herschel's contributions to solar science. The cloud-like character which he attributed to the radiant shell of the sun, first named by Schröter the photosphere, is borne out by all recent investigations. He observed its mottled or corrugated aspect, resembling, as he described it, the roughness of the rind of an orange, showed the faculae or elevations or heaped up ridges of the disturbed photospheric matter, and threw out the idea that spots may ensue from an excess of the ordinary luminous emissions. A certain imperial gas was, he supposed, very much as Wilson had done, generated in the body of the sun, and rising everywhere by reason of its lightness made for itself, when in moderate quantities, small openings or pores abundantly visible as dark points on the solar disk. But should an uncommon quantity be formed, it will, he maintained, burst through the planetary regions of clouds, and thus will produce great openings. Then, spreading itself above them, it will occasion large shallows (penumbræ), and mixing afterwards gradually with other superior gases, it will promote the increase and assist in the maintenance of the general luminous phenomena." This partial anticipation of the modern view, that the solar radiations are maintained by some process of circulation within the solar mass, was reached by Herschel through prolonged study of the phenomena in question. The novel and important idea contained in it, however, it was at the time premature to attempt to develop. But though many of the subtler suggestions of Herschel's genius passed unnoticed by his contemporaries, the main result of his solar researches was an unmistakable one. It was nothing less than the definitive introduction into astronomy of the paradoxical conception of the central fire and hearth of our system, as a cold, dark, terrestrial mass wrapped in a mantle of innocuous radiance, an earth, so to speak, within, a sun without. Let us pause for a moment to consider the value of this remarkable innovation. It certainly was not a step in the direction of truth. On the contrary, the crude notions of Anaxagoras and Zeno approached more nearly to what we now know of the sun than the complicated structure derived for the happiness of a nobler race of beings than our own by the benevolence of 18th century astronomers. and yet it undoubtedly constituted a very important advance in science. It was the first earnest attempt to bring solar phenomena within the compass of a rational system, to put together into a consistent whole the facts ascertained, to fabricate, in short, a solar machine that would in some fashion work. It is true that the materials were inadequate and the design faulty. The resulting construction has not proved strong enough to stand the wear and tear of time and discovery, but has had to be taken to pieces and remodeled on a totally different plan. But the work was not therefore done in vain. None of Bacon's aphorisms show a clearer insight into the relations between the human mind and the external world than that which declares truth to emerge sooner from error than from confusion. A definite theory, even a false one, gives holding ground to thought. Facts acquire a meaning with reference to it. It affords a motive for accumulating them and a means of coordinating them. It provides a framework for their arrangement and a receptacle for their preservation, until they become too strong and numerous to be any longer included within arbitrary limits, and shatter the vessel originally framed to contain them. Such was the purpose subserved by Herschel's theory of the sun. It helped to clarify ideas on the subject. The turbid sense of groping and viewless ignorance gave place to the lucidity of a possible scheme. The persuasions of knowledge is a keen incentive to its increase. Few men care to investigate what they are obliged to admit themselves entirely ignorant of. But once started on the road of knowledge, real or supposed, they are eager to pursue it. By the promulgation of a confident and consistent view regarding the nature of the sun, accordingly, research was encouraged, because it was rendered hopeful, and inquiries were shown a path leading indefinitely onwards where an impassable thicket had before seemed to bar the way. We have called the terrestrial theory of the sun's nature an innovation, and so, as far as its general acceptance is concerned, it may justly be termed. But, like all successful innovations, it was a long time brewing. It is extremely curious to find that Herschel had a predecessor in its advocacy, who never looked through a telescope, nor indeed imagined the possibility of such an instrument, who knew nothing of sunspots, was still, mistaken assertions to the contrary notwithstanding, in the bondage of the geocentric system, and regarded nature from the lofty standpoint of an idealist philosophy. This was the learned and enlightened Cardinal Cusa, a fisherman's son from the banks of the Moselle, whose distinguished career in the church and in literature extended over a considerable part of the 15th century, 1401 to 1464, in his singular treatise De Docta Ignorantia. One of the most notable literary monuments of the early Renaissance, the following passage occurs: "To a spectator on the surface of the sun, the splendor which appears to us would be invisible, since it contains, as it were, an earth for its central mass, with a circumferential envelope of light and heat, and between the two an atmosphere of water and clouds and translucent air." The luminary of Herschel's fancy could scarcely be more clearly portrayed. Some added words, however, betray the origin of the Cardinal's idea. "The earth also," he says, "would appear as a shining star to any one outside the fiery element." It was in fact an extension to the sun of the ancient elemental doctrine, but an extension remarkable at that period, as premonitory of the tendency, so powerfully developed by subsequent discoveries, to assimilate the orbs of heaven to the model of our insignificant planet, and to extend the brotherhood of our system and our species to the farthest limits of the visible or imaginable universe. In later times we find Flamsteed communicating to Newton, March 7, 1681, his opinion that the substance of the sun is terrestrial matter, his light but the liquid menstruum encompassing him. Bode in 1776 arrived independently at the conclusion that the sun is neither burning nor glowing, but in its essence a dark planetary body, composed like our earth of land and water, varied by mountains and valleys, and enveloped in a vaporous atmosphere. And the learned in general applauded and acquiesced. The view, however, was in 1787 still so far from popular that the holding of it was alleged as a proof of insanity in Dr. Eliot when accused of a murderous assault on Miss Boydell. His friend, Dr. Simmons, stated on his behalf that he had received from him in the preceding January a letter giving evidence of a deranged mind, wherein he asserted that the sun is not a body of fire, as hath been hitherto supposed, but that its light proceeds from a dense and universal aurora, which may afford ample light to the inhabitants of the surface beneath, and yet be at such a distance aloft as not to annoy them. No objection, he saith, ariseth to that great luminary's being inhabited. Vegetation may obtain there as well as with us. There may be water and dry land, hills and dales, rain and fair weather, and as the light, so the season must be eternal. Consequently, it may easily be conceived to be by far the most blissful habitation of the whole system. The recorder, nevertheless, objected that if an extravagant hypothesis were to be adduced as proof of insanity, the same might hold good with regards to some other speculators, and desired Dr. Simmons to tell the court what he thought of the theories of Burnet and Buffon. 8 years later, this same extravagant hypothesis, backed by the powerful recommendations of Sir William Herschel, obtained admittance to the venerable halls of science, there to abide undisturbed for nearly 7 decades. Individual objectors, it is true, made themselves heard, but their arguments had little effect on the general body of opinion. Ruder blows were required to shatter a hypothesis flattering to human pride, of invention in its completeness, in the plausible detail of observations by which it seemed to be supported, and in its condescension to the natural pleasure in discovering resemblance under all but total dissimilarity. Sir John Herschel included among the results of his multifarious labors at the Cape of Good Hope a careful study of the sunspots conspicuously visible towards the end of the year 1836 and in the early part of 1837. They were remarkable, he tells us, for their forms and arrangement, as well as for their number and size. One group measured on the 29th of March in the latter year, covering, apart from what may be called its outlying dependencies, the vast area of 5 square minutes, or 3,780 million square miles. We have at present to consider, however, not so much these observations in themselves as the chain of theoretical suggestions by which they were connected. The distribution of spots, it was pointed out, on 2 zones parallel to the equator, showed plainly their intimate connection with the solar rotation, and indicated as their cause fluid circulations analogous to those producing the terrestrial trade and anti-trade winds. The spots in this view of the subject, he went on to say, would come to be assimilated to those regions on the earth's surface where for the moment hurricanes and tornadoes prevail, the upper stratum being temporarily carried downwards, displacing by its impetus the 2 strata of luminous matter beneath, the upper, of course, to a greater extent than the lower, and thus wholly or partially denuding the opaque surface of the sun below. Such processes cannot be unaccompanied by vorticose motions, which, left to themselves, die away by degrees and dissipate with the peculiarity that their lower portions come to rest more speedily than their upper, by reason of the greater resistance below, as well as the remoteness from the point of action, which lies in a higher region, so their centers, as seen in our waterspouts, which are nothing but small tornadoes, appear to retreat upwards. Now this agrees perfectly with what is observed during the obliteration of the solar spots, which appear as if filled in by the collapse of their sides, the penumbra closing in upon the spot and disappearing after it. But when it comes to be asked whether a cause can be found by which a diversity of solar temperature might be produced corresponding with that which sets the currents of the terrestrial atmosphere in motion, we are forced to reply that we know of no such cause. For Sir John Herschel's hypothesis of an increased retention of heat at the sun's equator, due to the slightly spheroidal or bulging form of its outer atmospheric envelope, assuredly gives no sufficient account of such circulatory movements as he supposed to exist. Nevertheless, the view that the sun's rotation is intimately connected with the formation of spots is so obviously correct that we can only wonder it was not thought of sooner, while we are even now unable to explain with any certainty how it is so connected. Mere scrutiny of the solar surface, however, is not the only means of solar observation. We have a satellite, and that satellite from time to time acts most opportunely as a screen, cutting off a part or the whole of those dazzling rays in which the master orb of our system veils himself from over-curious regards. The importance of eclipses to the study of the solar surroundings is of comparatively recent recognition. Nevertheless, much of what we know concerning them has been snatched, as it were, by surprise under favor of the moon. In former times the sole astronomical use of such incidents was the correction of the received theories of the solar and lunar movements. The precise time of their occurrence was the main fact to be noted, and subsidiary phenomena received but casual attention. Now, their significance as a geometrical test of tabular accuracy is altogether overshadowed by the interest attaching to the physical observations for which they afford propitious occasions. This change may be said to date in its pronounced form from the great eclipse of 1842. Although a necessary consequence of the general direction taken by scientific progress, it remains associated in a special manner with the name of Francis Baily. The philosopher of Newbury was by profession a London stockbroker, and a highly successful one. Nevertheless, his services to science were numerous and invaluable, though not of the brilliant kind which attract popular notice. Born at Newbury in Berkshire, April 28, 1774, and placed in the city at the age of 14, he derived from the acquaintance of Dr. Priestley a love of science which never afterwards left him. It was, however, no passion, such as flames up in the brain of the destined discoverer, but a regulated inclination, kept well within the bounds of an actively pursued commercial career. After traveling for a year or two in what were then the wilds of North America, he went on the Stock Exchange in 1799, and earned, during 24 years of assiduous application to affairs, a high reputation for integrity and ability, to which corresponded an ample fortune. In the meantime, the Astronomical Society, largely through his cooperation, had been founded. He had for 3 years acted as its secretary, and he now felt entitled to devote himself exclusively to a subject which had long occupied his leisure hours. He accordingly, in 1825, retired from business, purchased a house in Tavistock Place, and fitted up there a small observatory. He was, however, by preference a computator rather than an observer. What Sir John Herschel calls the archaeology of practical astronomy found in him an especially zealous student. He re-edited the star catalogues of Ptolemy, Ulugh-Beg, Tycho Brahe, Hevelius, Halley, Flamsteed, Lacaille, and Meyer, calculated the eclipse of Thales and the eclipse of Agathocles, and vindicated the memory of the first Astronomer Royal, but he was no less active in meeting present needs than in revising past performances. The subject of the reduction of observations, then, as we have already explained, in a state of deplorable confusion, attracted his most earnest attention, and he was close on the track of Bessel when he made acquainted with the method of simplification devised at Königsberg. Anticipated as an inventor, he could still be of eminent use as a promoter of these valuable improvements, and carrying them out on a large scale in the Star Catalogue of the Astronomical Society, published in 1827, he put, in the words of Herschel, the astronomical world in possession of a power which may be said without exaggeration to have changed the face of sidereal astronomy. His reputation was still further enhanced by his renewal, with vastly improved apparatus, of the method first used by Henry Cavendish in 1797 1798 for determining the density of the earth. From a series of no less than 2,153 delicate and difficult experiments, conducted at Tavistock Place during the years 1838 1842, he concluded our planet to weigh 5.66, as much as a globe of water of the same bulk, and this result, slightly corrected, is still accepted as a very close approximation of the truth. End of Chapter 3, Part 1.